Really interesting research papers today, focusing on the tiny world where molecules meet metal.
That's right. And our goal really is to get into what happens at that fundamental level. It's about this specific, quite dramatic interaction.
We want to understand how these organic molecules and metal surfaces actually, talk to each other.
Hmm.
Because that connection is critical for making things like OLEDs or solar cells work properly.
Absolutely essential. The performance of so many next-gen electronics, flexible screens, better solar cells, even molecular memory, it all hinges on getting this interface right.
And today we're zooming in on one particular pair, a molecule called nickel tetraphenyl porphyrin, or NiTPP. Sounds impressive.
It is. It's a real workhorse molecule. Very versatile.
And it's interacting with a standard copper surface, Q100. The sources we have suggest, well, some pretty surprising things happen.
Oh, definitely. We're talking first about the molecule getting physically distorted in a major way. It changes shape quite drastically.
And second, there's this unusual electronic reaction, a charge transfer that's apparently way beyond what you'd normally expect.
Exactly. It fills up energy levels you wouldn't think could be filled. But maybe first, why focus on porphyrins at all?
Good point. Why are they so important?
Well, they're kind of foundational. If you look at promising organic tech-sensitive gas sensors, organic spin valves, transistors, LEDs, solar cells, porphyrins or something derived from them are often right there at the heart of it.
Okay, so they're a key building block.
They really are. Think of them as like a fundamental part of the architecture for these organic devices.
And their function, the reason they work in these devices, it comes down entirely to charge transfer, right? That electrical handshake between the metal and the molecule.
Precisely. It's all about electrons moving into or out of the molecule's key energy levels, what we call the frontier orbitals, the HOMO and LUMO.
Highest occupied molecular orbital and lowest unoccupied molecular orbital.
Got it.
If you control that flow, you control the device's function. Simple as that, in principle. In principle. But the sources say getting a clear picture of this is tough.
It really is, especially when there's a strong chemical bond forming, like we suspect here. Your standard tools, spectroscopic techniques like UPS or NXIFS, they often struggle.
Why is that?
Well, the signals can get muddled, or
Mhm.
sometimes the theoretical models we use, the density of states calculations, they rely on approximations that just don't capture the full complexity of that strong bond at the interface. It gets messy.
Okay, so standard tools have limitations. How did the researchers figure out this structure in this case then? They used scanning, tunneling, microscopy, STM, and DFT.
Density functional theory, yeah. Computational modeling. First, the STM results. They showed something pretty neat right away.
What's that?
Order. These NiTPP molecules didn't just land randomly. They formed these incredibly well-ordered layers packed tightly together.
Like molecular self-assembly.
Exactly. They even formed two distinct domains, mirror images of each other, rotated just slightly, about 8 degrees, relative to the copper's crystal structure. LED experiments confirmed this long-range order.
So they line up neatly. But you mentioned distortion.
Mm-hmm.
Where does that come in?
That comes from the closeness. The DFT calculations figured out the most stable spot for the molecule to sit the hollow site on the copper grid. And in that spot, the molecule's main body, the central part called the macrocycle, is forced incredibly close to the copper surface, like really, really close.
How close are we talking?
Just 2.0 angstroms?
Well, it's extremely short for this kind of molecule-metal interaction. It signifies a strong chemical bond, what we call chemisorption. It's not just resting there, it's locked on tight.
2 angstroms. Okay, that sounds like it would definitely cause some stress.
It does, a lot of stress. And that forces this dramatic shape change.
Yeah.
To keep that central macrocycle flat and maximize contact at that tiny distance.
The rest of the molecule has to give.
Exactly.
Yeah.
The 4 phenyl groups, these sort of side ligands attached to the macrocycle, think of them like the molecule's feet. They get brutally pushed upwards, tilted and twisted away from the surface. So the main body is flat against the metal, but the feet are sticking up in the air.
That's a great way to picture it. They measured the angles, a tilt angle around 140 degrees and a twist near 70 degrees. It's a significant contortion.
Wow. And this bending actually makes the whole layer chiral. You can see that.
You can. The way they tilt breaks the symmetry, so the layer isn't superimposable on its mirror image. And yes, that pattern, that chirality, shows up in the STM images. It's quite distinct.
So the molecule basically mangles itself to make this super tight bond. Fascinating.
But that mangling, that distortion, creates a big problem for actually seeing the important electronic stuff.
Right, because we just used SPM to see the structure.
Hmm.
How does that structure now hide the electronics? You called it an STM blind spot.
Okay, so imagine the STM tip scanning over the surface. What does it see most prominently?
Ah, the part sticking up the most, the phenol feet.
Exactly. The STM images show these four bright spots, these lobes. Those are the phenol rings tilted upwards. They dominate the picture because they're extended out.
Yeah, and the important part,
Yeah.
the macrocycle.
It appears as this dark patch, a depression, right in the middle. Because it's smashed down so close, just 2 angstroms away, the STM tip can't really resolve its electronic states properly. The contrast is swamped by those big phenol rings.
So the STM sees the feet, but the electronic brain, the macrocycle where charge transfer happens, is basically invisible to it.
Pretty much, you get a great picture of the distorted shape, but you can't probe the core electronic action where it matters most for devices.
That's a major roadblock then. If you can't see the HOMO and LUMO on the macrocycle, how do you know what's happening electronically? How do they get around that?
They needed a different tool, something that could look past the topography. They used a technique called photoemission tomography, or PT.
Photoemission tomography. Sounds complex.
It is pretty advanced. It's done using something called microangle resolved photoemission spectroscopy, or MARPS for short, instead of just mapping the surface height like STM.
It maps the electrons coming off.
Essentially, yes. It measures the energy and the angle at which electrons are ejected when you shine light on the sample. By collecting that angular distribution, you can reconstruct the shape and energy of the molecular orbitals they came from.
Like taking an X-ray of the orbitals themselves,
Yeah.
bypassing the physical shape.
That's a good analogy. It allowed them to directly see the electronic states of that hidden macrocycle, the ones the DFT calculations predicted should be there.
Okay, so they could finally see the electronic brain.
Yeah.
And what do they find about this unusual charge transfer you mentioned?
Well, remember that super close 2.0 A distance? That indicated a really strong interaction.
Right, the chemisorption.
And that strong bond led to a huge amount of electron charge transferring from the copper substrate into the NiTPP molecule.
Okay, some transfers expected, but this was more.
Much more. It wasn't just, an electron hopping into the lowest available empty state, the LWMO. It was like opening the floodgates. Yeah, the electron transfer was so significant, it didn't just fill the LUMO. It filled multiple, normally unoccupied molecular orbitals. The data confirmed occupancy all the way up to a LUMO plus 3.
Wait, LUMO, LUMO plus 1, and LUMO plus 3 were all filled with electrons from the copper.
Confirmed. Experimentally observed. LUMO plus 1, which are degenerate, meaning same energy, and LUMO plus 3, all occupied.
That's wild. Usually you talk about maybe the LUMO getting involved in these interfaces, filling 3 levels above the HOMO. That seems unprecedented.
It's certainly highly unusual and points to extremely strong hybridization between the molecule's orbitals and the metal's electronic states. It's like the copper is forcing the molecule to accept electrons into levels that are normally empty and quite high in energy.
So the molecule isn't just borrowing an electron, it's undergoing a fundamental electronic change because it's touching the copper so strongly.
That's a really good way to put it. It's almost an electronic identity shift.
Right.
And the beauty of the PTRPS technique is that it's so precise. They could pinpoint specific peaks in their energy spectra bumps in the data at certain energy values and say with confidence, okay, this peak at 0.15 eV, that's the LUMO plus 3 state, this one at 0.98 eV, that's the LUMO-LUMO plus 1 pair, and this one deeper down at 1.73 eV, that's actually the HOMO-1 state.
So they match the experimental energy signatures directly to the specific orbitals predicted by the theory.
Exactly. It provided unambiguous experimental proof, validating those complex hybrid functional DFT calculations that were needed to even predict such a strong effect. Simpler models wouldn't have captured it.
Incredible. But is it just a one-way street? Copper gives electrons to the molecule. End of story. The sources mentioned something else, a pushback.
Right. It's a bit more complex. There's a negotiation happening. While you have this significant charge flowing into the molecule's LUMOs,
There's also a charge going the other way.
there's also some charge donation back from other parts of the molecule to the substrate. It's this pushback effect. So electrons go in, but some density shifts back out.
Ah, a two-way flow then, like a charge redistribution.
Precisely. The net result of this complex exchange, this push and pull, is the formation of an interface dipole. It's like creating a tiny little voltage right at the junction.
And does that dipole matter?
Oh, absolutely. The sources note it actually reduces the work function of the system. That's the energy needed to pull an electron out. Lowering it can be really important for device efficiency, like getting electrons into an organic LED easily.
So this whole dramatic process, the distortion, the flooding, the pushback, it all culminates in changing a key electronic property of the interface.
Exactly. It's a tightly coupled structural and electronic story happening in that tiny 2 angstrom gap.
Okay, let's step back then. We've seen the structure, the electronics, the weirdness. What's the big takeaway here for people designing these kinds of devices?
I think the biggest lesson is about the tools and the approach. You simply couldn't understand this NiTPP on copper system with just one technique.
You needed both the STM and the photoemission tomography.
Absolutely. They complemented each other perfectly. STM showed you the physical consequences, the ordered layers, the bent feet, the structural part of the story, but it couldn't see the electronic core.
And the ARP-based PT came in and revealed that hidden electronic structure, the flooded LUMOs, the HOMO1, the actual charge transfer happening on the macrocycle.
Right. So the message is, when you have these strongly interacting, strongly hybridized interfaces where the molecule really bonds and maybe distorts, you have to use multiple techniques. One method will likely have blind spots that another can fill.
Simple models or single experiments just won't cut it if you want the full picture.
Not for these strongly coupled systems, no. If we want to actually engineer better devices based on these interfaces, we need to be able to see the whole picture, structure, and electronics, feet and brain.
So, to recap for everyone listening, we saw this NiTPP molecule get forced incredibly close, just 2.0 angstroms to the copper. This closeness caused a massive distortion, bending the phenyl feet up at almost 140 degrees.
A really extreme structural change.
And electronically, this led to an equally extreme charge transfer, flooding the molecule with electrons from the copper, filling orbitals all the way up to UMOL +3.
Which required cutting-edge photoemission tomography to even observe, because the structural distortion hid the electronic action from the STM.
It's a fantastic story of how structure and electronics are deeply intertwined at these interfaces, and how standard tools can sometimes miss the most critical part.
It definitely pushes the boundaries of both measurement and understanding.
And leaves you with a final thought. To really get what's going on with a molecule on a surface, especially when it bonds strongly, you need ways to see both its physical feet touching the metal and its electronic brain, the core states. This work shows that sometimes the most vital information is completely hidden. So the question is, what other molecular systems might we be misinterpreting right now, simply because we only have half the picture?